So what we've seen so far is that this birthday attack violates privacy of counter mode encryption in a somewhat non-trivial way. So the thing to take away is that when you're encrypting a number of messages that is 2 to the power half of the block length of the block cipher, then you will compromise privacy of those messages. That means you need to pick block ciphers where 2 to the power half of the block length is pretty big. For AES, that would be 2 to the power 64, which is nice. But for DES and triple DES, it's only 2 to the power 32, which is not safe. Now, that's just one attack. In our broader objective of determining whether CTR and CBC mode satisfy IND-CPA security, we are not yet done, because all we've seen is that there is some kind of non-trivial attack. But for all I know, there's an even better one. Maybe there's a very fast constant time attack. Maybe there's an attack that works with advantage q cubed over 2 to the n. And all of these things would be quite damaging. It's difficult now to see how we could resolve this situation, in the sense that either somehow conclusively determine that there isn't a better attack, if we can't find one. And the interesting answer is that that is actually possible. We are going to say with some degree of confidence that this birthday attack is really the best IND-CPA attack that exists. How can we possibly do that when we don't have any enumeration of all the possible attack strategies? We couldn't. It's an infinite set of strategies. The way we do it is that we actually have some kind of proof metric, and it actually shows that if you consider an arbitrary adversary making q queries to the left or right oracle, then its advantage is at most the formula shown here. In this formula, sigma is the total number of blocks across all encrypted messages. That means that if you look at the messages sent in left or right queries, across the queries they may have different lengths. You simply add up all those lengths and divide by the block cipher block length. If you consider that this adversary happened to ask queries consisting only of single block messages, then you notice that you recover this formula over here, because sigma would just be the same as q. So the takeaway from this is that if you're using AES in counter mode encryption, then you effectively can encrypt up to 2 to the 64 message blocks. How you distribute these blocks across different messages doesn't really matter that much, but as long as the sum of the lengths of all the messages is not more than 2 to the 64, you're relatively okay, and after that you're relatively not okay. So that gives us some confidence that that counter mode actually works. Now that perspective at a high level has underlying it a more interesting and nuanced result. This is what's an example of a proof of security. It's a mathematical justification of the security of a scheme, in this case of counter mode. In this class, it's the objective that we should know what these kinds of things are, what they mean, how to interpret the statements, and to understand why they matter, what are their strengths and limitations. But we won't go so far as actually establishing and proving them. That's done in the graduate class. But let's try to understand what a statement saying that counter mode is provably secure would look like. So the way it starts is we take a family of functions, call it E. This is viewed as given, and we're willing to assume that it's secure. We exploit heavily here our prior development of definitions and analyses for block ciphers by saying that the assumption we make on E is PRF security. That's what makes this theorem work. Key recovery security would not be enough to give the conclusion here. And so this is a very powerful application of that assumption. Once we have E, we can consider the symmetric encryption scheme given by counter mode, and that's now a well-defined and fixed scheme. And I want to say, how well does an adversary do against this? And I want to say, well, it actually doesn't do too well. Of course, how well it does depends on its resources, and so that has to enter somewhere. So take an arbitrary adversary, not some specific piece of code that you wrote down, but any adversary out there. We don't restrict its strategy, but we do restrict its running time and the number of left or right queries it makes. In practice, this just means that there is a practical limit on computing time, and the users are not encrypting more than Q messages with the scheme. Let's further assume that the number of blocks across all the messages, meaning the sum of the number of blocks in each message, is at most sigma. And now I'm going to give an upper bound on the advantage of the adversary. Effectively, I'm going to say its advantage can't be more than something. What is that something? The main element is this over here, which is the thing we saw before. This says that this adversary's advantage can grow proportionally to the product of the number of things encrypted times the sum of the lengths of all the messages encrypted, divided by 2 to the power of the block length, but not more than that. And so this is effectively what's saying that the birthday attack is the best possible. You can't get an advantage better than this when your resources are restricted to Q and sigma. Okay, but there's more to it, and the more you start seeing the need for it when we ask a question like, wait a minute, what happened to the block cipher E? It's also part of this picture. And clearly, if this is lousy, if it's like the identity function or some really bad thing, counter mode is not going to be secure. So how does that show up in this result? Well, it shows up with this additional term. It says, actually, you can do a little better than violating than this probability over here. And but the extent you can do better is limited by the strength of your block cipher. This is expressed in what's called a reduction. Given our adversary A, I build an adversary B violating PRF security of the block cipher, and the advantage of that adversary appears here. If E is a very good PRF, then this advantage we would expect to be small, and so the sum of two small things would also be small. If E is not a good block cipher, this could be big. At that point, all the theorem is saying is, well, I can't tell you much, because the advantage would be bounded by some big thing, and well, that's generically true anyway. So that's what it says. The way you interpret this then is to say that the PRF security of the block cipher, if assumed to be true, implies the IND-CPA security of counter mode encryption with this quantitative relationship. But this is a nice thing to have, and it tells us that effectively this scheme is something we can use with some confidence that it works. And indeed, that has led to increased usage of the scheme. So I did say we wouldn't prove it, but it doesn't hurt actually to give you a little bit of intuition about why counter mode is in fact going to be secure up to the birthday bound, because it emanates from something quite simple. Effectively, it's saying that counter mode is just a way of creating a huge one-time pad. So how does this arise? Well, let's just for simplicity look at this particular case. We are considering an adversary A trying to violate IND-CPA, so it's going to call its left or right oracle some Q times, and we're going to assume that for simplicity, all the messages have exactly M blocks. So the sum of the lengths of the sum of the number of blocks across the messages is just M times Q. And that's really for notational convenience, not for anything else. This adversary is arbitrary. It's not a particular one. As per the theorem statement, it's arbitrary. And yet I want to somehow argue that its advantage is not that big. So let's consider the ciphertext returned by the left or right oracle to the adversary. We know how they're computed. They're computed based on the block cipher and the key in counter mode, and they encrypt either the left or the right message, and they have m+1 blocks, where m is the number of blocks in the message. Okay. The way we start thinking about this is that we move to a kind of a thought experiment world. In this experiment, the block cipher is removed and replaced by a random function. You remember what a random function is? It's just this enormous table or a game in which every time you ask a question, you just get back a random reply. This random function is effectively now our key. We have, as it may seem, an absolutely gigantic, impractical sized key. But counter mode can be written in that way. All you do is you substitute e sub k with this random function, and the scheme now looks as shown over here. This thought experiment scheme no longer involves any block cipher. It's a purely probabilistic combinatorial object. But we can ask whether INDCPA holds for this scheme. If an adversary plays the left or right game, the scheme is well defined. Does it win? Does it get an advantage or not? And we will first start by arguing that it's okay to restrict attention to this thought experiment. How does that happen? Because we exploit the fact that E is assumed to be a pseudorandom function. Intuitively, the fact that E is a pseudorandom function means that how well the adversary does against this thought experiment scheme is pretty much the same as how well it would do against the real scheme where Fn is E sub k. Of course, that needs a very careful proof, which is where the reductions come in, but intuitively that's what a PRF means. Once we've done that, we'll look at the thought experiment, and the claim is that unless something goes wrong, encryption is being done effectively just with a one-time pad. What is the thing that could go wrong? It's that as you perform different encryptions, you twice use the same input to Fn across different messages. Why is that a bad thing? Because random functions are consistent. If you twice call on the same input, they give the same reply. If that doesn't happen, every p sub I that you ever see is a purely random string independent of anything you've seen before. So this p sub I thing is just a big one-time pad. So effectively, we're doing one-time pad encryption of each and every message encrypted. And that obviously, or by what we've said before, is going to be extremely secure. The adversary will actually have a zero advantage in that case. Putting these two things together, you come back up with the theorem we had. Again, that was not a proof. It's just a very, very high-level hint at what's going on. And you're not responsible, by the way, for any such proofs, but you are responsible for understanding the statements of the theorems and their implications. The same kind of result holds for cipher block chaining. We don't have to go through the details, but the statement looks very similar. This little exercise asks you to take what we've done and kind of interpret it verbally, explain it to someone. It's a good way to see that you understand the implications beyond the technical elements over here. And this is another exercise, a little bit different from what we've seen before. It asks you to actually build a scheme satisfying certain properties.